Now I can define my norm T prime as supremum of norm T prime x plus m such that norm x plus m is less than or equal to 1 for all x belongs to n. Okay. So using the definition of T prime, we can write this as norm T prime is equal to supremum of norm T of x such that norm x plus m is less than or equal to 1 for all x belongs to n. This is how we can use the definition. I can write the reason as because T prime of x plus m is equal to T of x, right? So now call this as equation number 4. Okay, so what are the things we have now? X belongs to n and m belongs to m. This implies x comma m belongs to n. I can say that x comma m belongs to n. Why? Because m is subspace of linear subspace of your normed linear space n. So from this we can write x plus m belongs to n, right? So now this is one part of the proof. Next I will consider the definition of norm T. So using this definition, we can write supremum of norm T of x such that norm x is less than or equal to 1 and your x belongs to n, right? So again we know that T of x is equal to T prime of x plus m. From that we can write supremum of norm. So if you consider x plus m, since we know that x plus m is also belongs to n, I can write this as norm T of x plus m such that norm x plus m is less than or equal to 1 and your x belongs to n, m belongs to null space m, right? As we know that m belongs to m, this implies T of m is equal to 0, right? Because m is our null space and a mapping of this will be equal to 0 vector. So I can write T of m is equal to 0. Now if you consider T of x plus m, since T is linear, I can write this as T of x plus T of m, and we know that T of m is 0. So this will be equal to T of x. That's why I can write norm T of x as norm T of x plus m. If they have not given m as a null space, then I cannot map this vector to a 0 vector. Then it may be equal to T of x plus m or may not be equal. But since they have given that m as a null space, I can say that T of x plus m will be equal to T of x. Okay. So now our norm T will be equal to supremum of norm T of x such that norm x plus m is less than or equal to 1 and m belongs to null space m. I will call this as equation number 5. Now observe your equation number 5 with your equation number 4. Both are equal, isn't it? So now from equation 4 and 5, I can say that norm T prime is equal to norm T. So this is how we will say that T induces a linear map T from n by m to n prime. Okay. Now let's move to the next concept, that is algebra. Okay. First let's see the definition of algebra. We can define an algebra as it is a linear space. An algebra is a linear space whose vectors, that means the vectors of linear algebra, can be multiplied in such a way that they have given for some 3 conditions. If those 3 conditions are satisfied, then I can say that it is an algebra. Okay. So let's see those 3 conditions. The first condition is x into y z is equal to xy into z, where x, y, z all are the vectors of your linear space. And the second condition is x into y plus z is equal to xy plus xz, or you can write that x plus y into z, which is equal to xz plus yz. These two comes under, if you check these two properties, you can say that these two are distributive properties, isn't it? One is right distributive, another one is left distributive. And the third case is alpha into xy is equal to alpha x into y, and this is equal to x into alpha y, where alpha is your scalar. So any vector which satisfies these three conditions, then we can say that those vectors are of a linear space is said to be algebra. Okay. Along with these three properties, if a vector satisfies one more property, that is norm xy is less than or equal to norm x into norm y. If any vector satisfies these three factors, along with that if it satisfies this fourth condition also, then that particular algebra is called as normed linear algebra. I hope you can understand the difference between algebra and normed algebra. So algebra is said to be normed linear algebra along with these three conditions if the vector satisfies the fourth condition also. If the fourth condition is not satisfied, means that particular vectors are said to be algebra itself. Okay. So now let's move to one more definition, that is Banach algebra. I can define Banach algebra as a complex or real Banach space. Okay, a complex, or we can say real Banach space is said to be Banach algebra if it is a normed algebra. That means any Banach space which holds the property of normed algebra, then we can say that as a Banach algebra. This is how we define our Banach algebra. Using this definition, we have some of the theorems to prove. Let's see one by one. Okay. So the first theorem statement says that B of n denote the set of all bounded linear operators on normed linear space n. Then B of n is a Banach algebra with the algebraic operations T1 plus T2 of x is equal to T1 of x plus T2 of x. T1 T2 of x is equal to T1 of T2 of x, and A T1 of x is equal to A T1 of x, and they have given one more, that is norm T is equal to supremum of norm T of x, such that norm x is less than or equal to 1 and your x belongs to n, where T1 and T2 which is coming from B of n. Okay, this B of n is nothing but your Banach space. First, what we have to prove, this Banach space is a Banach algebra. We have to prove this first. And they have given one more thing to prove, that is also multiplication in B of n is jointly continuous. These two things we supposed to prove. So first let's see how we can prove this theorem. According to this theorem, which we have already proved, we know that B of n comma n prime is already a normed linear space, or it holds the property of linear mapping, right? So now if you check these conditions, the linear property condition we need not to prove because it is already proved, and by looking at the condition itself we can say that it is a the operations satisfies the condition. So now what I will do is, in order to prove B of n as a normed algebra, first I will prove the distributive property. Okay, that distributive property is nothing but T1 of T2 plus T3 of x. I have to prove this is equal to T1 T2 plus T1 T3 of x, right? So this will be equal to, we can write this as T1 into T2 plus T3 of x. So now this is nothing but, I will retain T1 as it is, T2 of x plus T3 of x. So now this is nothing but T1 into T2 of x plus T1 into T3 of x. Again this will be T1 T2 of x plus T1 T3 of x. So I can rewritten this as T1 T2 plus T1 T3 operating on x, right? So this is nothing but your distributive property which supposed to be proof for algebra, right? T1 T3 of x. So next what we have to prove? In order to say this as a Banach algebra, we have to prove that norm T1 T2 is less than or equal to norm T1 into norm T2, right? We have seen in the definition. If I prove till here, then I can say that the given space is a Banach algebra. But we have to prove it is a normed, just an algebra. But we have to prove that B of n is a normed algebra. In order to say it is a normed algebra, I have to prove this condition also, right? So now let's define our norm T1 and T2. Norm T1 T2 is equal to supremum of norm T1 T2 of x such that x belongs to n and your norm x will be less than or equal to 1. So now this will be equal to supremum of norm T1 into T2 of x such that x belongs to n and norm x is less than or equal to 1. So now this will be obviously less than or equal to supremum of norm T1 into norm T2 of x such that x belongs to n and your norm x will be less than or equal to 1. I will take norm T1 outside into supremum of norm T2 of x such that x belongs to n and your norm x will be less than or equal to 1. So now this whole thing is nothing but norm T2. So your LHS part will be less than or equal to norm T1 into norm T2, right? So we can say that norm T1 T2 is less than or equal to norm T1 into norm T2. From this I can say that B of n is Banach algebra. We have one more part to prove, right? We have to prove that multiplication is jointly continuous in this space. So let's move to that part now. So let's define Tn converges to T and Gn converges to G. Since it is a Banach space, obviously there exists a limiting point or a converging point. So I have defined that Tn converges to T and Gn converges to G, where we can say that this Tn and Gn are coming from the space B of n, right? So now I will consider norm Tn Gn minus Tg. So this will be equal to Tn into Gn minus G plus Tn minus T into G. How I can write this? Before that, what I have done is I have just added and subtracted your RHS part by Tn into G. Okay, that means this can be rewritten as norm Tn Gn minus Tg plus Tn G minus Tn G minus Tg. In this, if you group the terms and if you take common, you will get in this way. The same procedure we have applied and we proved one of the theorem in your remark, if you remember. So now if you split this modulus, you will get an inequality. So norm Tn into norm Gn minus G plus norm Tn minus T into norm G. So obviously, since we are in a Banach space, this whole term converges to 0 as n tends to infinity, and this whole term converges to 0 as n tends to infinity. We have already considered that Tn converges to T and Gn converges to G as n tends to infinity, right? So from that I can say that norm Tn Gn minus Tg converges to 0 as n tends to infinity, right? So from this I can say that Tn Gn converges to Tg. This is nothing but multiplication is jointly continuous in B of n. So from this I can conclude that multiplication is jointly continuous in the space B of n, right? Hope this theorem is clear to all. Let's move to the next theorem. The statement of the next theorem says that suppose that the Banach space is the direct sum of the linear subspaces M and N. They are considering the direct sum of the linear subspaces M and N. So we can denote our direct sum as M plus N, right? B is equal to M plus N, and let Z is equal to X plus Y be the unique expression of a vector Z in B. So in B, in Banach space B, they are expressing Z as a unique representation, okay? That is sum of two vectors X plus Y, and X and Y are coming from the linear subspaces M and N. We have to show that a new norm can be defined on a linear space B by norm Z prime is equal to norm X plus Y. This is what we supposed to prove. From this data we have to show that there exists a new norm, and I can express that new norm as a norm X plus norm Y, and we have to verify that it is actually a norm. In order to prove that it is actually a norm, what I have to do? I should prove the four properties, right? Then if B prime symbolizes the linear space equipped with this norm, prove that B prime is a Banach space if M and N are closed in B. That means we have to prove first, we have to show that there exists a new norm. After that I have to prove that this new norm is a normed linear space. Then we have to prove that there exists B prime as a Banach space, okay? This B prime is a Banach space. That means we have to consider a Cauchy sequence, and we should prove that there exists a converging point in the same space. These three parts I have to prove now, okay? So we have B as a direct sum of M and N. M and N are closed. These two things are given in the data, and they have given one more thing, that is I can represent Z as a unique representation, that is X plus Y, where X belongs to M and Y belongs to N, right? So we have to prove that there exists, from this there exists one more norm, that is norm Z prime is equal to norm X plus norm Y. This is what they have already given. So first what I will do is For this new norm, the space is B prime. Don't get confused. Your B and B prime both are same sets. Okay. So I can denote B prime norm prime. This is my new function now. That's it. Okay. Where B prime is equal to B. Now let's consider elements as Z, Z1, Z2, and this belongs to B prime. But we know that I can represent Z as X plus Y, and this X plus Y are coming from the direct sum M and N, and that belongs to B. So B is equal to B prime. Okay. If Z is equal to X plus Y, then I can write Z1 as X1 plus Y1 and Z2 as X2 plus Y2, right? Now your X, X1, X2 belongs to the space, closed linear space M, and Y, Y1, Y2 belongs to N, right? So the first case is obvious. We know that norm Z prime is always greater than or equal to 0 for norm X, norm Y is greater than or equal to 0. This implies norm Z prime is greater than or equal to 0. We can write in this way. So the next case is I have to prove that norm Z prime is equal to 0 if and only if Z is equal to 0, right? This is my second case. Norm Z prime is equal to 0 if and only if Z is equal to 0. How can I prove this? If I consider norm Z prime is equal to 0, this implies that norm X plus norm Y is equal to 0. So from this we can write that norm X and norm Y will be equal to 0. That is X is equal to 0 and Y is equal to 0. So from this I can say that Z is equal to X plus Y, which is equal to 0. So the second condition is also true. Now let's move to the third condition, that is norm Z1 plus Z2 whole prime is equal to norm X1. I can write this as norm X1 plus Y1 plus X2 plus Y2 whole prime. So this can be rewritten as, if I split my modulus, I will get inequality. So norm X1 plus X2 plus norm Y1 plus Y2, right? So this will be less than or equal to norm X1 plus norm X2 plus norm Y1 plus norm Y2. Now group the terms. Norm X1 plus norm Y1 plus norm X2 plus norm Y2. So from this is nothing but norm Z1 prime, and this is nothing but norm Z2 prime. So your norm Z1 plus Z2 whole prime will be less than or equal to norm Z1 prime plus norm Z2 prime. This is our third condition. And the fourth condition is norm alpha Z prime. I can write this as, I have to prove this is equal to mod alpha into norm Z prime, right? So I can write alpha Z as alpha into X plus Y. This is nothing but alpha X plus alpha Y, right? So norm alpha Z whole prime is equal to norm alpha X plus norm alpha Y. This will be mod alpha norm X plus mod alpha into norm Y. I can take mod alpha as common, and this is norm X plus norm Y. So from this we can write that norm alpha into, mod alpha into norm Z prime. This is my fourth condition. So from this I can say that B prime comma norm prime function is a norm. Alright. So one more part I have to prove, that is B prime is a Banach space. I will continue with that in the next session. Okay, thank you.